Hello and welcome to the second live stream for Astro Pi Mission Space Lab 2526. My name is Fireball Fergus and I am delighted to be joined by the Astro Pi Mission Control team from the Raspberry Pi Foundation, plus very special guests from the European Space Agency, Nina Van Tent and Lev Theodoropoulos. Let's meet the team. Please welcome Galactic Geraint, Rocket Richard, Neutron Nick, and special guests Supernova Nina and Lunar Lefteris. Hello everybody, and great to have you all back again for another Astro Pi live stream. Let's kick off with some quick introductions, starting with our very special guest host, Nina from ESA Education. Welcome Nina, great to have you here. Could you tell us what you do and where you are based?
Of course, I work at ESA Education, and at ESA Education, we offer many opportunities to both educators and students. For example, teacher training and school-based projects such as Astro Pi. And our aim is to use space to support STEM education in Europe through our Azero network. And the Zeros are our national European space education resource offices that organize trainings and events locally. So make sure to check out what Azero organizes in your country on astro-pi.org/azero-pages. You can also see the link appear in the screen below. And I'm here with my colleague Lev Theodoropoulos. So Lev, could you also introduce yourself?
Yes, hello everyone. I'm Lev. I'm also part of the ESA Education team, and I'm based at the European Security Center and Education Center in Belgium.
And I'm based in the Netherlands at ESTEC, which is ESA's Research and Technology Center. And here we have a broad range of clean rooms and facilities where satellites are developed and tested to survive the harsh environments of space. And the fun fact is that one of the Astro Pi flight tests was performed here as well. And we'll tell you all about the importance of testing your programs in this webinar.
Great to have you here today, Nina and Lev. Thank you for joining us. And now let's quickly meet the Astro Pi Mission Control team at Raspberry Pi, starting with Galactic Geraint.
Hello everyone, hope you're having a nice time. I'm Geraint and I am based in Edinburgh.
Hi there, I'm Nick and I'm based between London and Cambridge in the UK.
And I'm Fergus, Astro Pi Program Manager, and I live near Cambridge in England. Great to have everybody here today. So now that you've met all our panelists, you'll know who's going to be answering your questions later, because today's live stream is all about you, the incredible teams and mentors taking part in Mission Space Lab this year. Please let us know where you are joining from with your team name and country in the chat, and we'll do some shout outs shortly. This year is a very special year because Astro Pi is celebrating its 10th anniversary of sending your code to the International Space Station. At 11:03 on the 15th of December 2015, former European Space Agency astronaut Tim Peake launched from the Baikonur Cosmodrome in Kazakhstan on a Soyuz rocket bound for the International Space Station. 2 Raspberry Pi powered Astro Pi Mark I computers were waiting for him in the Columbus module of the ISS, ready to be set up for an experimental education activity called Astro Pi. Since those first experiments ran, over 160,000 young people have sent their code into space through the Astro Pi Challenge. Tim Peake and some of the Astro Pi team were at the London Science Museum to celebrate the anniversary in December. We hope that you will be able to celebrate with us by sending your code into space for this special anniversary year. Now, over to Nina for more information about today's live stream.
Thanks, Fergus. So today's live stream is focused on any technical challenges that you may have experienced while doing your mission. And for the next hour, we are going to answer all of the questions that you have sent in and share some top tips for running a successful Mission Space Lab. Plus, if we have time at the end, we'll answer some questions from the chat. So if you haven't sent one in yet, please add any questions to the chat and we'll come to those later on. And at this stage in the Mission Space Lab, you may have already started working out the flow and structure of your program, writing it, and maybe even doing some testing. And perhaps you have even submitted and want to know what happens next. And we'll cover all of that today to get you and your teams in the best possible position to have your code sent to the International Space Station in the spring of 2026. But first, let's do some shout outs, Fergus. Who do we have on the chat today?
Well, Nina, today we've got people joining from all over Europe, which is fantastic to see. We've got Matthew Kerr from France. Hello there. We have Besta Gloriosi from high school in Italy. Welcome. We have Ale Aistar from Romania, Miroslav Kubera from Czech Republic, and we have Timisoara from Romania as well. So yeah, please let us know where you're joining from. Post it in the chat, and we'll give you a little shout out shortly. But thank you. It's fantastic to have so many teams joining us from around the world today. Here at Astro Pi Mission Control, we receive questions about Mission Space Lab to our inbox all year round, and we see some similar issues come up for teams. One of those issues is how to calculate your final speed estimate correctly and avoid a division by zero error. We thought we'd start our session today by addressing this and give you all a solution for this particular issue. So here's Galactic Geraint with a short video about why this error happens and how to solve it so your code runs without errors.
One of the most common issues we see with Mission Space Lab submissions is the zero division error. These errors can be frustrating. They are avoidable, but if they aren't handled, they can cause a program to crash completely, something we've seen happen before on the ISS in the past. In this video, we'll explain what these errors are, how they happen in Mission Space Lab submissions, and how you can prevent them. What is a zero division error? A zero division error happens when you try to divide a number by zero. In mathematics, dividing by zero is undefined because there isn't a clear answer. For example, while we know that 8 divided by 2 is 4, it isn't clear how many times 0 goes into 8. Because of this, Python considers dividing by 0 a mistake and raises a zero division error. Where do these errors happen in submissions? You should be mindful of this type of error whenever your code performs a division. Generally, in Mission Space Lab submissions, we see this error happening in the speed calculation function. This function calculates the speed of the ISS using the formula speed equals distance over time. The distance is the number of pixels between features found in consecutive photos, and the time is the time difference between the images. If the time between the two photos is 0, then Python will raise a zero division error. But why is the time between photos 0 when the Astro Pi has only one camera? The answer involves how time data is stored and rounded. Most teams use the datetime digitized field from the image EXIF metadata to find out when it was taken. This field only stores time to the nearest second. It doesn't include microseconds. If you take two photos very quickly, in less than a second, both might be rounded to the same second and you end up with a zero division error when trying to calculate the speed. For example, consider this timeline, where t is the time in seconds since the start of the program running. As you can see, the first photo is taken at t equals 2.5 seconds. The second photo is at t equals 3.4 seconds. The difference between photo 1 and 2 is 0.9 seconds. Rounding to the nearest second, where 1 to 4 are rounded down and 5 to 9 are rounded up, both photos end up with a time of 3 seconds. If you were to use the difference between the two photos to calculate the speed now, you would end up with 0 seconds in the bottom of the fraction, the denominator, and consequently a zero division error. This is how the error appears in Mission Space Lab submissions. The datetime digitized times are rounded to the nearest second, so the difference between photos can be 0 and cause the program to crash unless special action is taken. How to avoid the error? Fortunately, There are several strategies you can use to stop your program from crashing in the event of a zero division error. The most common way to stop a crash is to use a try except statement. The try except statement is a bit like a way to set up a backup plan in case something goes wrong. It consists of a try block, one or more except blocks, and an optional finally block. Python tries to run the code inside the try block. If an error occurs, then instead of stopping immediately, Python instead checks to see if there is an except block matching the type of error. If there is an except block matching the error, then Python will run the code in the except block. Otherwise, the program will start to terminate, but not before running the code in the finally block, which is always executed if it exists. The finally block is generally used for cleanup, such as closing resources and open files. So, if we want to have a backup plan in case of a zero division error and stop the error from crashing the program, we can put the calculate speed function inside a try block and deal with the zero division error in an except block. Now, instead of crashing, our program will print divided by 0 when the time between consecutive photos is 0. It can be tempting to put your whole program inside a try statement, but generally it's best to keep the try block as short as possible. While the try except statement is very powerful and is something we would recommend you use in your submission, it does not really fix the underlying issue. To do that, you need to change your code to make sure that the time difference between photos is never 0. This can be done by adding a sleep command from the time standard library module to wait at least 1 second between photos. Another option is to use a different time source field. You can record the time yourself using the datetime.now function from the datetime module when you take the photo, rather than relying on the image metadata. This gives you more precision and helps avoid rounding issues. Even though the times recorded will not be the exact times the photos were taken, this won't matter when calculating the speed, where we're only interested in the time difference between photos. Writing a separate function that takes a picture and stores the time is a good way of keeping the time intervals consistent. In conclusion, writing defensive code like this is a fantastic way to reduce the chances that your program will crash on the ISS. You may want to consider some other common errors listed in the Common Mistakes section of the Mission Space Lab Creator Guide. Finally, don't forget, it is essential that you test your program before submitting it. The best way of doing that is to run it using the Astro Pi replay tool, which you can do online at this address.
Thank you, Gowan. We hope that helps to answer your divide by 0 errors. That issue really captures the challenge of preparing to run experiments for real on the space station. It's so important to test your programs and get them performing as best you can before you submit your code.
That's right. Running your programs on the Astro Pi computers aboard the space station is going to give you slightly more variety for your calculations than the guides and the Astro Pi replay tool output. So make sure you are happy with how your program is working and that it's giving you an output as accurate as you can. So Fergus, team, I think it's now time for some questions.
That's right, Nina. Let's get into it. Panelists, are you ready? Okay then. So our first question today is, are photos captured at daytime or nighttime from the ISS? And I'd like to nominate Neutron Nick to answer this question for us.
Thank you, Fergus. The short answer is that all Mission Space Lab programs will be run during daylight hours. You're not going to be able to see very much at nighttime, unfortunately, using the camera that we have on board the Astro Pis on the ISS. Geraint has written some code that's going to make sure that every program is scheduled to run when the ISS is in daylight, so you don't need to worry about them running at night. However, one thing that we can't guarantee is that your program is going to run when there are clear skies, or that when it's over land rather than over sea. So when you're testing your program, it's a good idea to make sure it works well with cloudy images, just plain sea and coastline, and a wide variety of surface and lighting conditions. And you can get hold of all of those examples from the replay tool. So if your program works with mixed and imperfect images, it's much more likely to support to succeed when it's in orbit.
Thanks, Nick. Then I'm going to ask the next question. So this question is from Team New School in France. And they are asking, when I use the camera to determine the ISS speed, I use the formula for the ground sampling distance. Could you tell me where to find or provide me with the parameters of the image width, the focal length, and the sensor width? So in short, how do I calculate the ground sampling distance? And this question I would like to ask to answer by Geraint.
Okay, thank you for this question. So on the screen, you will see an image of the Netherlands that was taken back in 2023 or 4, I think, from the node window. So notice across there that's about 500 kilometers. So for people that haven't come across the term ground sampling distance before, what is it exactly? Well, it's the distance between two adjacent pixels on the screen. So if you see that line across is about 500 kilometers, then the answer is about 500 kilometers divided by the number of pixels it spans. So if you have a ground sample distance of 10 meters, that means that each pixel corresponds to about a 10 meter by 10 meter square on the Earth's surface. So to answer how to calculate the ground sampling distance, you will need to refer to a formula which is shown on screen. So the Astro Pi Creator Guide already publishes the ground sampling distance for the Astro Pis. So if you aren't sure, I would refer to that, and you will see that it's got an answer of 12,648 centimeters. What does that mean? It means each pixel captured by the Astro Pi camera corresponds to a square with sides 126 meters long, which is over the size of a football pitch, which is quite an amazing thought. So if you are just following the Astro Pi ISS speed project, all you need to remember is to use that number. But let's dig into a bit of the detail now to find out how that number was calculated. So at the top of the screen, you'll see the formula. GSD equals, which is ground sampling distance, equals the height times the sensor width divided by the focal length times the image width. So as you may know, the height of the ISS is not constant. It's somewhere in between 400 and 420 kilometers. So for our magic number, the 12,648, we used a H value of 408 kilometers. But if you want to know the exact height at the current time your program is running, you can take the snippet of code that you see in the middle. The focal length of the Astro Pi is 5 millimeters. That's a property of the lens that won't change. The sensor width is 6.287 millimeters, and the image width is 4,056 pixels. So you could either put those numbers into an online calculator or into the equation you see on the screen, and the answer you will get is a GSD of 12,648 centimeters. So I hope that answers your question.
Brilliant. Thank you, Geraint, and it's great to see Team New School joining this live stream this up.
Okay, I think that Fergus has to restart a little bit, so I will take over the next question, which I will answer. So our next question is the speed of the ISS constant? And Geraint already gave a little bit of a hint to that, but I will explain more. So in short, no, the speed of the ISS is not perfectly constant. The ISS continuously experiences small amounts of atmospheric drag, even at a at an altitude of 400 kilometers, where the atmosphere is very, very thin. And the drag slows down the station slightly, which in turn causes it to lose altitude, typically around 100 meters per day. So to counteract this loss of altitude, the ISS performs regular reboost maneuvers, usually every few weeks. And during these maneuvers, onboard thrusters fire their engines to increase the station's speed to raise the altitude. And as a result of that, the ISS altitude generally varies between 400 and 420 kilometers, what Gerrit was also just mentioning. And while this is a very small variation, it could matter for teams that are looking for ways to further optimize the accuracy of their speeds or the ground sampling distance calculations. So instead of using a fixed value, and thus a fixed ground sampling distance, you can also calculate the ground sampling distance dynamically based on the ISS's current altitude. And that is with the formula that Gerrit was just showing on the screen. And then I'm not sure if Fergus is back, but I will continue with the next question. So if we only use coordinates data from the Astro Pi computers on the ISS, will that be enough to make our calculations? And I would like to ask Nick to answer this one.
Thank you, Nina. This is a great question. So the quick answer for this is no. That would not be accepted for Mission Space Lab. It is a really good project idea, though, and I would encourage you to explore it if you're interested. But getting a speed estimate just using coordinates is something that you can do using the Skyfield library, and that is actually something that you could do on Earth. You don't need to run that on the International Space Station. And the opportunity of Mission Space Lab is so special because you get to access real equipment on the International Space Station. We want to give that opportunity to as many teams as possible. So for that reason, we're only going to accept submissions that do use the Astro Pi hardware, such as the sensors or the cameras. You have to use those in some way. Another thing that I would encourage you to do is to make the most of the opportunity is to record as much data as possible, even if you're perhaps only going to use like the inertial sensor or the magnet sensor. Just record as much data as you can from all of the sensors on board, because you get to keep up to 42 photos. You get to keep all of the sensor data that you or your school could do further science on and analyze for other projects in the future. And who knows, if you get a really good set of images and sensor data, and we use a similar window next year, then your data might end up as an example run in the replay tool for teams to test their projects on in the future.
Thank you, Nick. Then we have a next question. Are the images on the replay tool the same as we can capture from the ISS? And I'd like to ask Gerrit if he can answer this one.
Yes, the images from the replay tool are from a previous mission on the International Space Station. In fact, the ones that are currently online on the website are full resolution images captured from the Window Observation Research Facility window in 2023. They should be the same as what you'll capture when you use the default settings from PyCam 0, which means that they're full resolution. Of course, the weather and conditions below may be different, though, so there's some variation to be expected.
Thank you, Gerrit. Okay, so we continue with the next part. So some great questions already. Thanks to everyone who has sent them so far. If you haven't sent any in yet, please post your questions in the chat and we'll answer as many as we can in the time we have. But now we're going to take a short pause from the questions, and Lefteris from ESA Education is going to share some interesting information for you about where the Astro Pis will be positioned on the ISS and whether this has any effect on your data readings. Over to you, Lef.
From the International Space Station, astronauts have one of the most extraordinary views of Earth. The ISS orbits our planet every 90 minutes. That means astronauts get to see a sunrise and a sunset about 16 times a day. This is exactly why Astro Pi experiments work so well there. The ISS became a real scientific laboratory into space, and Astro Pi allows students to use it in order to observe Earth from orbit. When we talk about Astro Pi's location, we usually mean just a few specific windows on the ISS. From the outside, the ISS looks like one big structure. For Astro Pi experiments, only a small number of windows are actually used. Not every window is suitable, and not every location is available. These are the main locations we're talking about: the node windows and the Window Observational Research Facility, or as we call it, WRF. All of them look at the nadir direction and give us amazing views of Earth, but they are built differently, and that leads to some interesting effects in the data and images. So a very natural question is, do these differences actually affect the results of the Astro Pi experiments? If Astro Pi is in different places or facing a different direction, does that change what we measure? When students start thinking about this, they often assume that one of the Astro Pi sensors must be responsible. After all, Astro Pi has many sensors: temperature, humidity, pressure, light, and so on. Most of the time, the sensor students point to is the gyroscope. So let's take a closer look at it. What does it really measure, and what does it not measure? To explain this properly, we will need some help. And who better than Tim Peake, the first ambassador of the Astro Pi?
I'll just get this gyroscope here, and it's just a toy gyroscope really, but of course in zero gravity, if you knock it, it's going to tumble, it's going to move around like any object up here does. However, if I get this spinning, just give me a second. So once the gyroscope is spinning, you can just see how stable it becomes. And however I knock it, it's not going to change its plane. It's going to remain in the same plane. I can put it physically into a different plane and tap it again, but it will still hold that same plane, and it's much more stable. So it just gives you an idea of how we use spin stabilization and gyro stabilization for control on board the International Space Station.
What Tim Peake showed very clearly is what a gyroscope actually does. It measures rotation and orientation, which way something is pointing. Even when Astro Pi is touched or moved inside the ISS, the gyroscope keeps the reference direction. But it never tells us how fast the ISS is moving. So, changing Astro Pi's location does not affect the calculation of the ISS orbital speed. Now, let's take a closer look at where these windows actually are. To do that, as astronaut Thomas Pesquet will guide us through the ISS. As we watch real footage from inside the station, we'll compare it with a 3D model so you can exactly see where the Astro Pi is placed. This is Node 2, also called Harmony. It's one of the busiest modules on the ISS, and this is where visiting spacecraft or vehicles dock. The nadir-facing window here looks straight down to Earth and gives the Astro Pi a direct view of the planet. Moving on to the WRF window, you can see on the bottom right how the Astro Pi looks when it operates from this window. Something really interesting shows up when we compare Astro Pi images from different windows. In the node windows, there is a heat rejection cover with an 8-inch opening. Because this cover sits a few inches away from the window, it creates a circular crop effect in the images. In WRF, there is no heat rejection cover, so Earth fills the entire image. And this year, we're lucky enough to use the WRF window, giving us the best possible pictures. But Astro Pi isn't the only thing that's happening on the ISS. The station is a very busy place, with astronauts working, equipment moving, and operations happening all the time. For example, astronauts sometimes need to perform spacewalks. They leave the station and work on the outside to do maintenance or repairs, all while moving at around 8 kilometers per second around the Earth. At the same time, the robotic arm called Canadar might be operating, or vehicles may be approaching or departing the ISS. As you can understand, all of these activities can temporarily affect Astro Pi experiments and observations. But don't worry, this is all carefully planned and we make sure you still get the highest possible data quality. And finally, since we're celebrating Astro Pi's 10th anniversary this year, I'd like to end with something fun. Here's a video showing how Astro Pi can even be used as a virtual candle, a small celebration floating into space. That's all on my side. Thank you. Back to you, Tim.
Excellent. Thank you, Lev. That was some really useful advice for your teams, and because we want you to avoid any basic errors that might stop you from having your code run in space as much as possible. So now we've got some more questions from you in the chat and some we received before the live stream. So let's get cracking on those for the remainder of this session. Fergus, could you read out the first question? Oh, I'm afraid you're muted.
There we go. Trying to get back into the live stream. So let's start with a question that we've received from the chat. And this is from Ala Eister. And the question is, can the code capture multiple pictures at the same time, at the same time interval? For example, 4 pictures every 3 seconds, or is it limited to 1 or 2 pictures? And so I'd like to nominate Nick to answer this question for you.
Thank you, Fergus. So I want to make sure that I understand the question firstly. Basically, yes, you can take multiple pictures. You can take multiple pairs of pictures and run your code on them to get a speed estimate from that pair, and then just keep taking pictures for the duration of your 10 minutes. You are limited to downloading 42 of your pictures. You can only keep 42 photos to download at the end of Mission Space Lab. Once you get them, you can do things like average out your results. You can do things like disregard any that seem erroneous in some way in order to try and get a more accurate result. But you can't actually take 2 photos at the same time. It's only got 1 camera, and it takes about 1 second for the Astro Pi to take a full resolution image, which we do recommend that you guys stick to. So yes, multiple images, and with an upper limit of about 42. I hope that helps.
Brilliant. Thank you very much, Nick. And thank you very much for that question as well. We have another question from Matthew, which I think is from Team New School again. And I think we haven't completely understood your question, which is, I use sin of latitude. I want to use the heart rotation correction. So I think what we would ask you to do, if you could email us at contact@astro-pi.org with a bit more information, and then we'll be able to troubleshoot that for you and explore that in a little bit more detail than we're able to do live today. But we're very happy to help you out with that. So please could you send us your email, and I think we do have a banner at the bottom of our screen right now if you want to make a note of that email address, and then we can help you out with that one. In the meantime, we've got another question that we've received prior to the live stream, and this one is about the Coral dongle. And the question was, the Coral dongle doesn't seem to be working with the latest version of the Raspberry Pi OS. Will it work on the Flight OS on the International Space Station? And I'd like to nominate Geraint to answer this.
Yeah, that's a very astute observation there. So unfortunately, Google has stopped supporting the Coral dongles. The last update to the software that they run was in fact in 2021, and we've been trying our best to keep it working since then. Without support from Google, though, the Coral dongles no longer work on recent versions of Linux operating systems, and in particular, the Coral dongles will not be usable on the Flight operating system this year. You can still run TF Lite models on the ISS, on the Astro Pis, but they'll be using the CPU instead of the Coral accelerator and using Google's latest Python library, AI_edge_light_RT, instead of the now unsupported TF Lite runtime and Pi Coral libraries, both of which are no longer usable. You can get more information on how to use the AI Edge Light RT library and how to use machine learning if you check out the creator guide.
Thank you, Garant, for that answer. We also have another question, which is, we don't have much time to complete our program. What would you suggest we do? And I would like to ask Nick if he can answer this.
I can, thanks, Nina. So one thing we were wondering about this, and at the Raspberry Pi Foundation, we decided to run a hackathon, which is condensing Mission Space Lab down into one sort of more condensed session over 1 or possibly 2 days. And it was very successful when we did it, and we created a resource so that you might want to recreate the same thing. We should have there's a short link on the screen now. So if you have a look at that, you should be able to get the sort of lesson plan for that. The idea is that each team splits into 2 smaller groups, and each focuses on a different part of the problem. So one group would work on the camera side, making the Astro Pi take the photos, save the image files, and adding the file names and all the useful metadata and other sensor data perhaps that you want. The other group would be working on the data analysis side. So on the Raspberry Pi project site, we have something called the ISS speed test activity, which is very similar to some of the stuff that some of you will be doing in Astro Pi. It's making a speed estimate of the ISS from 2 historical photos, like that provided by the replay tool. Once those 2 halves of the team have kind of created their working components of parts of code, the team kind of comes together to merge the 2 pieces of code and then tests and refine the full program. So that is a way that you can condense down many sessions of Mission Space Lab into one sort of intensive go. We found it worked very well, and it was really good fun.
Thank you, Nick. Okay, then we're going to the next question. What's the best way to test your program if you don't have an Astro Pi? Garant, could you answer this one?
Yes. As Nick just mentioned about the Astro Pi replay tool, that is the simplest way to test your program. It provides you a series of historic images and data for you to use to simulate your code as if it were running on the International Space Station, even though you might not have access to an Astro Pi yourself. So to use it, you can go to the link below, rpf.io/replay.
Thank you, Garant.
Fantastic. Thank you, Garant.
Oh. Yeah, you go ahead, Fergus.
I think maybe let's just do a quick prompt to see if anybody else has any more questions that they'd like to pose us while we're on the live stream on the chat as well. So if you do have any burning questions, then please do post them. We do have a bit more time if we receive them. Otherwise, I thought I would just do a quick reminder of the date for Astro Pi, because we had an email recently about where to find a timeline. So if you go to the Mission Space Lab landing pages on the website, that's astropi.org/Mission Space Lab, you can find all of the dates that you need and information that you need for submitting your programs on time. So the deadline for submissions for this year is Monday, the 16th of February. And we need to receive all of the submissions by 12 noon Central European time. So please make sure you've registered your teams and submitted your code by then. There's also on the website, you'll find a downloadable timeline with dates if you need it. And there's also lots of resources available from the astropi.org/resources page, including links to the various guides and links to the Zero pages where you can find some help from the zeros in your countries. So do have a look and check out those resources if you need any help. But for now, it doesn't look like we've had many more questions come in. So I think perhaps we will wrap things up. Thank you for all of the questions that teams have sent in today and before the live stream as well. We hope that we've been able to answer everything and give you some tips for achieving flight status and having your code run on the International Space Station.
Yeah, and remember that you can contact Astro Pi Mission Control anytime on contact@astro-pi.org if you have any other questions. The deadline, as Fergus was also just mentioning, but I will repeat it, for Mission Space Lab is 12 o'clock at noon Central European time on Monday, the 16th of February. So make sure you don't miss the deadline.
Fantastic. Thank you, Nina. I noticed we've got another post from Matthew. Just a reminder that the output that you need to get with your programs is in kilometer. It must be 5 significant figures and in kilometers per second. If you do have any more clarifications, Matthew, please do email us and we will get back in touch with you and hopefully get your program working as soon as possible. But thank you for joining today.
And good estimates.
This live stream. Sorry, Nick.
I said they're good estimates. What Matthew's posted in the chat.
They are. They're very good estimates. This live stream will be available to watch again on YouTube once we end this broadcast. So, plus you can watch the live stream that we recorded in November, getting started with Mission Space Lab. From everyone here at Astro Pi Mission Control, we wish you the best of luck with your missions. Good luck, everybody. And it's bye for now.
Goodbye.
Bye, everyone.
Bye-bye.
Bye.